Welcome to the lectures on modern digital communication techniques. So, we have started discussing modulation methods, in which we have just started discussing about pulse amplitude modulation. In pulse amplitude modulation, we have identified that there is a pulse whose amplitude gets selected based on the input bit sequence, that is the information sequence. And we have also mentioned earlier in the beginning of our discussion on modulation, digital modulation techniques, that in contrast to analog communications, in digital communication there is a choice from a finite set. So, I would again like to revisit that particular aspect before we proceed further, because in the previous lecture we have just discussed that there is a sequence of bits which are used in selecting the particular choice of waveform. So, that is the part where you are mapping the bits to the waveforms, or you are mapping symbols to waveforms, or you are basically mapping bits to symbols. So, that is why we identified that this particular part of the communication system could also be known as symbol mapper. So, this is sometimes a bit confusing, and hence I will try to re-explain some of the things so that it clarifies that what exactly is being used to select the waveforms. So, if you consider a typical analog waveform, let us say this, and we have a carrier, let us say this. So, if you were to modulate the carrier with this waveform, what you would typically get is the envelope, and you would get the analog amplitude on the carrier, right. Whereas, if we are talking about a digital communication system, the first step that we generally do is to sample the source. So, when you are sampling the source, let us take for example the particular waveform as the source signal, and due to sampling we are going to get, let us say so we will be sampling at a rate which is more than twice the maximum frequency content. So, let us imagine that these are the samples, right, and then these pass through a quantizer. So, if we have certain definite levels, so we could imagine as if you are at this level, then you are at a level here, then you are at a level here, then again back there, back somewhere there, again there, again there. Something like this of the form. So, quantization means that instead of having continuum amplitudes, you are now having discrete amplitude levels, right. The next step in the process is that suppose there are certain number of levels, right. So, you would have to put some kind of coding method. So, if there are, let us say L levels, so you would need log base 2 of L as the number of bits. So, let us take for example L is equal to 16. In this case, this which could be used as B, we would say that B would be equal to 2, because L is equal to B is equal to 4, because L is equal to 2 to the power 4, right. That means there are 4 bits required to identify each level uniquely in a fixed coding. And then there could be source encoding, that would depend upon the type of encoder, as well as the variability of this, that means the entropy of this. Let us assume that these 16 symbols would on an average require 3 bits. Let us take for example, because of redundancy, suppose we have this. So, that means on an average we are going to get 3 bits per symbol, that means per sample, right. So, basically we are getting a sequence of bits where we are getting 3 bits on an average out. Now, this bit stream would go into the symbol mapper that we have just discussed in the previous lectures. So, for example, let us take pulse amplitude modulation, and for simplicity let us take m is equal to 2. Now, if we would remember what we discussed, that let am, that means for the amplitudes that we take, be 2m minus 1 minus m times d, where m is equal to 1, 2 up to capital M. So, here m takes a value of 2, that means m equals to 1 and 2. The result we got was A1 is equal to d, that means 2 minus 1, that is 1, minus 2, that is minus 1 times d, that is minus d, and A2 is equal to d. That means we have at our disposal to select from 2 levels. If this level is 0, this level would be minus d and this level would be plus d, right. And our symbol mapper could be designed in a way that 0 maps to minus d and a 1 maps to a plus d. So, in this case the symbol mapper output would be a minus d followed by a plus d followed by a plus d followed by a minus d followed by a plus d followed by a minus d followed by a plus d, a plus d and a plus d. So, that means this is corresponding to 0, this is corresponding to 1, 1, a 0, a 1, a 0, a 1, a 1, a 1. So, this is d, this is minus d and this level is of course 0, right. So, what we can understand from this is that these levels that the pulse amplitude modulator selects has nothing to do with these levels, right. Not in an exact sense, of course, these bit streams are generated because of these levels, but these levels do not map to these levels, right, because clearly you can see that we have used b bits over here and we have taken the example where it is 4 bits, whereas this symbol mapper is taking 1 bit at a time. You could also get things clearer if you consider that let our symbol mapper that is with us. Again, we will take the example of PAM, because that is what we have learnt, is let m is equal to 4. So, when I say m is equal to 4, this implies that there are 4 amplitude levels, right. So, if there are 4 amplitude levels, that means k is equal to log base 2 of m, which is equal to 2 bits. That means now we are going to select the amplitudes using 2 bits. So, if we are taking this sequence, so we have the input sequence 0, 1, 1, 0, 1, 0, 1, 1, 1. Suppose we have this sequence. So, we have to find what amplitude levels do we have. So, if we use the same method, so we are going to get A 1 is equal to 2 minus 1, that is 1, minus 4, that is minus 3, times d, it is minus 3 d. A 2, that is 4 minus 1, 3, minus 4, that is minus 1, minus 1 times d is equal to minus d. A 3 is equal to, that is 3 to 6, minus 1, 5, minus 4, that is 1, which is d, and A 4, you can now put 4 over here, 8 minus 1, 7, minus 4, that is 3 times d is 3 d, right. So, you have these levels. That means, we could say that this symbol mapper has levels. If I mark this as 0, this would be minus d, this would be minus 3 d, let us say. So, ideally speaking, this should be minus 3 d, and if this is d, then somewhere here should be 3 d, right. And in that case, these sequence would map to certain levels, like I would take 2 bits. So, these 2 bits have to be used in selecting an amplitude, 1 0 has to be used in selecting that. So, in the previous case, we have seen 0 would map to minus d, 1 would map to plus d. So, we could find a similar mapping. We could say 0 0 would map to this amplitude, 0 1 would map to this, 1 0 would map to this, and 1 1 would map to this. So, that means, whenever there is a 0 0, I will select minus 3 d, whenever it is 0 1, I would select this, whenever there is a 1 0, I would select this, whenever there is a 1 1, I would select this. So, now what happens, whenever there is a 0 1, I would go there and I would select minus d. So, now minus d would be selected. Now, please take a note that we have discussed in the previous lecture that since there are 2 bits used for the symbol duration, in that case the symbol duration would be equal to the duration of 2 bits, right. So, that means, this minus d would hold for a duration which is 2 t b, right, followed by you have 1 0. So, then you are going to get 1 0, then you have another 1 0, it should be like this, then you have 1 1, so which would be here, and then suppose we have a 1 0, let us say 1 0, that means you are back over there, right. So, now in contrast, if we compare the 2 waveforms that we have got, what we see is that this is the 0 level, same as the dashed line, and we have a 0 1 followed by 1 0 followed by 1 0 followed by 1 1, and let us say we have a 0 in all places, right, followed by 1 0. So, what we note is that this same sequence produced a different output waveform compared to this one, and in both the cases, since this bit rate was the same, this bit rate would also remain the same. The symbol duration has of course changed. So, here this is t duration, but it is producing different levels. Now, how we use it is another matter which we can continue to discuss. So, all I am trying to point out in this particular discussion is that the sequence that we get here, which is due to this, is used in a different way when it is sent to the symbol mapper. All I am trying to say is that these levels do not mean the output of PAM. So, never get confused with this. This is a typical confusion that we get among students. So, we should clarify that these levels are the levels of the quantizer, whereas these levels are the levels of the symbol mapper. So, this is something important that we should remember. Right. So, moving on further, once we have discussed this particular thing, what we can do is we can compute the energy. So, when you compute the energy of, let us say, m array PAM, if m is equal to 2, you have binary. If it is 4, you have 4 array, let us say, or 4 level PAM, 8 level PAM, and so on and so forth. So, if we are taking a look at the computation of energy for m array PAM, we would say EM is equal to integrate 0 to t, t is the symbol duration, Sm of t, that is the symbol, squared dt. So, this is the energy of the mth symbol, right. So, this would turn out to be half am squared 0 to t g squared t dt, and this is the energy of the pulse. So, you could clearly write it as half am squared Eg. So, where Eg is the energy of the pulse, right. So, now using this, we will be using this in one of the important calculations that is going to appear soon. So, moving ahead further, we could say that these particular signals are one dimensional. It will be clear very soon. Now, why we are calling it one dimensional? Because you are selecting only the amplitude of the signal, there is no other thing that you can select. So, there is a GT times cos 2 pi FCT, and you are having an AM on top of it. So, this AM is the only parameter that is changing, GT cos 2 pi FCT is remaining constant for the interval small t between 0 to capital T. So, we would generally write down Sm of t as some Sm, which is a coefficient, you can think in terms of a coefficient, times Ft. So, we would like to recall our discussion on Gram-Schmidt orthogonalization procedure, and there we had orthogonalized a set of signal using a new set of signals, which we would call it the basis signal, and then you could expand any signal using the basis signal by projecting the original signal onto the basis, right. So, whatever are the components on the basis would be used to denote in a vector notation. So, we have a similar form over here, and we could say where Ft is the function is root over 2 by Eg, because we are normalizing the energy, because if you take Ft squared, you are going to get Eg in the denominator, and this will be Gt squared. If you would integrate, you are going to get Eg in the numerator, Eg in the denominator, and they would cancel out each other, cos 2 pi FCT, and this would cancel out with this half. And in that case, we could write Sm is equal to Am times square root of Eg upon 2. So, if you would look at this signal, we have Sm, which is Am root over Eg by 2, and Ft, where this, so these two terms cancel out. You have Am Gt cos 2 pi FCT, which was the expression of SMT in the earlier discussion. So, this is valid for m equals to 1 to 3 up to capital M. Now, you could easily represent this Sm on a diagram like this, which we have been using, and we could say if we have two levels where 0 would indicate to a minus d, let us say, and this would indicate to plus t. So, you could represent the signal in this form, which we have already seen, and of course, this is with normalized energy. Now, at this point, it is crucial that we look at what kind of mapping that we do, because we are discussing the symbol mapper. We have already talked about two different kinds of symbol mapper, that means one which selects between two amplitudes and the one where there are 4 amplitudes levels. So, in the 2 amplitude level case, your life is simple. So, you could select the negative with 0, or you could also use this notation, and then things will be quite manageable, there will not be any differences. But if we look at the 4 level mapping, that means if we take the example that is here, then situation is pretty different, because you have several combinations. For example, if let us say this is 0, this is D, this is 3D, this is minus D, minus 3D, we have already identified one particular combination or mapping, right, which is indicated in this particular amplitude selection. So, this maps to this level, this maps to this level, and it is also indicated here, is also indicated here. Now, one might ask that what if I do this kind of a mapping, or what if I do this kind of a mapping, right, or maybe some shifted version. Finally, you might have this. So, the question that comes up is, out of these, which mapping would one choose? One could go for any other combination as well. So, I have taken 4 combinations, right. So, if we look at this particular way of arrangement, then we are basically talking about the mapping or we are talking about the symbol mapper, right. So, which symbol, so this is a symbol, would map to which amplitude level is the issue of discussion. So, you could do all possible combinations. Now, we would like to come back to a discussion of white noise. So, during the discussion of white noise, we talked about certain correlation properties. We should also discuss about the PDF, probability density function. So, for quadrature, that means the noise with I and Q components, the probability density function would be given by 1 by, for case of Gaussian noise, which we had actually studied, where x and y are the I and Q components or the quadrature components of the baseband equivalent noise, and we said the PDF would look like this, where sigma squared would be phi xx of 0. We have already discussed phi xx, phi yy, and I would not go back to them again, notations remain the same. So, that is why we have been saying always we will follow the notations. So, if we go by this density function, and since we have said that in case of Gaussian, because of the uncorrelatedness, you can say that they are independent, you can treat Px separately from Py, or Px and Py, the joint distribution is a product of the distributions, right. So, Px would be the one without the y component and Py would be the one without the x component. And typically the Gaussian distribution would have a PDF which would look like this, right. Let us say P of x, and this is 0, right, and this is x. This is how it would look like. So, now when we are sending these signals out into the channel, this gets affected by noise. We have already discussed that there is this additive noise. So, if we would see an example, that let us say we have these levels, these get affected by noise. So, noise gets added, right, and then what happens if we set a decision level which is halfway. That means if, so I should mark these levels, of course, that this is let us say minus D, minus 3D, D and 3D. In this case, if this is my decision level, so if the signal falls below this decision level, I would detect the signal level as D, whereas if it goes above this level, I would detect it as plus 3D. Similarly, if it would fall below this level, I would detect it as minus D. If it goes above the level, I would detect it as D. So, we are landing into the problem of errors. So, what we would like to highlight at this point is, because of noise, one would make a choice which is not the right choice. That means, you have sent a D, but because of presence of the noise fluctuations, you may detect it as plus 3D or you may detect it as minus D, because there is a decision threshold here, right. So, because of these colored fluctuations, if they fall below this threshold, instead of detecting it as D, and D had a particular symbol mapping. So, if we go by one of the particular mapping that we have used here, D had mapped to 0 1 and 3D had mapped to 1 1 and minus D had mapped to 0 1, this had mapped to 0 0. So, the implication goes like this, that if I make a mistake in detecting D as minus D, I would, instead of detecting, this is 1 0, this is, instead of detecting 1 0, I would detect as 0 1. Now, this would get me into error. Similarly, if I go on the higher side, instead of detecting 1 0, I would detect 1 1. So, at this point, we would come to a conclusion of this particular unit, this particular lecture, simply by stating that there is a possibility of mapping these symbols in a particular way, whereby you could reduce the potential chance of making more errors, right. Of course, there are a lot of techniques to reduce errors, and we will start the next discussion of how to select these mappings, whereby you can reduce the number of bits that go into errors. Thank you.